Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. This is lecture number 76. So in the previous lecture, we were discussing about the transformation of an asteroid to a meteorite, and we were looking at broad classifications of meteorite. In this lecture, we shall start with the following question. How do we determine the composition of a meteorite? Although, like I alluded to in the previous lecture itself, we're not particularly concerned about what all molecules are there. Broadly, we understand that there are going to be silicates and some organic molecules adsorbed onto the surface. Okay, but how they are determined is an important aspect. All right, it is that the answer to this question is that we do it via what is called as, along with the spectroscopic techniques that we discussed while on the modules of interstellar medium. As far as meteorites are concerned, the most important technique is what is called as mass spectrometry. So mass spectrometry is a technique via which, and notice it, this is not spectroscopy, this is spectrometry. Okay, METRY, not SCOPY. Okay. So it is via mass spectrometry that we detect and determine what all molecules are present in a meteorite. All right. One important difference between spectroscopy and spectrometry is that spectrometry is a destructive technique. This is a destructive. In other words, but spectroscopy is not. For example, what I'm trying to convey here is that when you analyze some meteorite via mass spectrometry, some amount of the sample is lost. Okay, right? We have a physical sample with meteorite, right? Because nature provides us with the meteorites. The physical sample is already in our labs. Okay, the meteorites can be analyzed by this technique called as spectrometry, wherein we do something to the sample and some part of the sample gets lost. Whereas with spectroscopy, that is not the case. Otherwise, how do you imagine detecting molecules which are somewhere in outer space, right? Just with the interaction of light with matter, which doesn't change the matter itself. That is the beauty there, right? So spectroscopy is not a destructive technique though. So please note this point. Spectrometry is a destructive technique which changes the nature of the sample, but that is still okay. Even though the sample is changed, we still understand what is the chemical composition of the sample. All right. But in spectroscopy, the sample itself is not changed. Please note this key point. So what is mass spectrometry? I will give you a very a brief overview of that. So in mass spectrometry, the idea in mass spectrometry is that you create ions from the sample, from the sample that you want to analyze. So what I've written here is you create ions from the sample to be analyzed, right? And then these ions are sorted in terms of their, when I say ion, typically it's a cation. Of course, you can also generate anions, but that is much harder. So in general, when I say ions, these are cations, right? So then these are sorted in terms of their mass, which is what we call as the as the M/E ratio. So once we know you create ions from the sample, right? When I say ions, see, you take some molecule M. Say, for example, you take a molecule M, right? While we create cation, you will be getting M plus. But this M plus undergoes further fragmentation. Typically, it gives rise to various fragments such as M1 plus, M2 plus, M3 plus, etc., etc. All right. So these are the ions which are sorted in terms of their masses, and the fragmentation pattern, right? Starting from this M plus ion. By the way, this is a capital M and these are all small m. If the handwriting was bad enough, please note it. This is a capital M and these are all small m. Small m1, small m2, and small m3. This is in capital case. All right. So this is the parent ion, and you get all these fragments which are produced from it. So these fragments are characteristic of any given molecule. So from this, even though we destroy the sample, we understand what the original sample is. All right. So this is how we we find the composition of what's in the meteorite. All right. Just one more point about mass spectrometry. It can be a separate master's level course, mass spectrometry. So I'll just tell you that there is one more technique called as mass spectrometry, via which the composition of a meteorite can be analyzed. For now, please be okay with that. All right. So the next point is that typically, how is mass spectrometry carried out? I will say, for example, you have the sample to be analyzed. You pass it through an ion source. So you pass it through an ion source. So the ion source can, it can be electrons, right? Highly energetic electron rays. It can also be, some sort of a laser, or it can also be some kind of a chemically induced, a combination of molecules and electrons. That is what is called as chemically induced. Okay, I'll just call it as CI. Okay, so these are the various ion sources, and then you have your sample collector or analyzer, or when I say sample, it's typically all the ions, right? Now notice that this particular sample collector or the ion collector, it needs to be in vacuum. Why should the vacuum be necessary here? Well, what is a vacuum? Recall from our discussion and discourse on the interstellar medium. Vacuum refers to a state of more or less no molecules. So see, we are generating highly energetic ions. If we have some, if you don't have vacuum here, in other words, if we have some molecules present in the sample collector, they might react, right? So therefore, your objective of understanding a fragmentation pattern from the parent molecule that you want to be analyzed, that the objective would be lost. Okay, so that is why it being in vacuum is important. And so this is all, this could be connected to a computer to give you the feed, okay, of the M by E peaks, etc., etc. So this is the simple setup. I mean, even saying the word simple is an overstatement here. It's a very rough, fundamental idea behind how mass spectrometry works. So this technique is used to understand the composition of the meteorites. Okay, so as far as meteorites were concerned, we have looked into how is a meteorite formed from an asteroid, and we looked at its composition broadly. And I told you that mass spectrometry is used to understand and find the composition of the meteorites. The next part, of meteorites that we'll be looking at is very interesting. Okay, I'll tell you what it is. It concerns some nuclear chemistry and how meteorites help with ascertaining or finding the age. Okay, right? The age of the solar system, the age of at least some parts of the universe, etc., etc. I will talk about that in this slide. Okay, this part of the board. So this module is going to be meteorites, nuclear chemistry, and the age of some parts of the universe. I'm not saying the complete universe, but some parts of the universe could be figured out from this. Okay, so this is what we'll be looking into next. All right, now before we actually talk about this, I want to ask you one very important question. Most of us here should be familiar with the idea of carbon dating, right? What is carbon dating? Well, a small detour before this. Okay, to get to here, that is to this point. Okay, a small detour. So the question I asked was, most of us are familiar with this idea called as carbon dating. Okay, carbon. What is the fundamental idea involved in carbon dating? Well, with this idea called as carbon dating, you can analyze and test how old any fossil is. Right? It can be plant fossil, it can be animal fossil, anything. What is the fundamental science behind this carbon dating? It is that your living beings, when alive, absorb the 14 isotope of carbon. What is the normal isotope of carbon? It is the 12 isotope, right? But we also absorb some 14 isotope, but when alive. So after death, the absorption of the 14 isotope stops. Okay, and absorption of 14 carbon stops after death. Okay, please note this point. But see, the normal isotope, the routine isotope of carbon is 12. So this is of course an unstable isotope. So what this particular isotope does is, it undergoes what is called as a beta decay. So this undergoes what is called as a beta decay by this process. Your 14C undergoes a beta decay. Beta is nothing but an electron, a fastly moving electron, referred to as this, plus 14 nitrogen, and this is going to be 1. Yeah, 14C6, and this is 17N7. And even though this should be -1, okay, it's an electron after all, right? See, for the sake of simplicity, I'll just write it down as an electron itself. Okay, a beta particle is nothing but an electron efficiently. Living beings absorb 14 carbon, and after death, death of not just human beings, of all the plants, animals, by whatever definition, once they stop living, the absorption of 14 carbon stops. But 14 carbon then continuously gets converted to your 14 nitrogen, which is a stable isotope. So this is unstable with what is called as a T-half. By T-half, I'm talking about the half-life. In other words, of roughly close to 5,700 years. Well, 5,700 is like unstable for us. Please note it. Okay, right? And it results in a stable nucleus of nitrogen. Okay, it slowly undergoes radioactive decay. This is a nuclear process, right? It's a nuclear transmutation. In fact, carbon is becoming nitrogen. Okay, while this happens, so I mean, consider a being. As long as it's alive, it constantly absorbs 14 carbon, which of course is always becoming transformed into 14 nitrogen. But by the time some entity dies, a living entity, a once living entity dies, then you no longer absorb 14 carbon, but instead everything becomes your 14 nitrogen. All right. So from the ratio of your 14 nitrogen present, right, one can determine, right, from the ratio of the 14 nitrogen present, from the amount, sorry, not ratio, from the amount of 14 nitrogen present, one can determine how much 14 carbon should have been there initially. should have been absorbed initially, and through that, and I'll continue from here. Okay, initially, comma, I'll go all the way up here, and through this, the age of the fossil or the sample could be obtained. But hey, there's a limitation, because the half-life, by half-life, I'm talking about the time it takes for half of the initially present 14 carbon to decompose into 14 nitrogen. That is what is called as the half time, which is denoted by the symbol T half. Half time. Okay, right? Sorry, not half time, half lifetime. Half time is a soccer term. T half is this half lifetime, right? Now it's more explanatory. So T half refers to the time it takes for half of this initially present sample to become the 14 nitrogen. Okay. So based on the knowledge of your T half, which can be experimentally determined, I'll come to that in a bit. Okay. And from the amount of, by calculating the amount of 14 nitrogen present in a system, because it is consistently getting formed from 14 carbon, you can determine the age of the sample. Now, this technique is valid for samples. It's valid for samples which are of the order of 50,000 to 60,000 years. All right, but what is the age of the universe? What is the age of the universe? Forget the universe. What is the age of the solar system? Any idea? Roughly? Well, this is just a general knowledge question. The age of the solar system is roughly, around like 4.5 into 10 to the power 9 years. Okay, this is roughly the time, right? But we're talking about samples which could be analyzed, which are only 60,000 years old. All right. So therefore, the same idea which is used in carbon dating, which is used to analyze samples, can also be extended. This is a nuclear chemistry, by the way, right? So the same nuclear chemistry notion can be extended to actually understand some parts of the universe itself. All right. And this is particularly helpful by analyzing meteorites. So we took this detour. We took this detour on carbon dating to connect you with the idea that in the same way, carbon dating is done to understand the age of a fossil sample, where the fossil, could be 50 or 60,000 years old, but not more than that, right? Only for that period of approximately 60,000 years is this technique valid, because the half-life is of the order of 5,700 years only. Okay, we need to determine the age of the solar system, etc., etc. While the principle may be the same, we need some other element, okay, and some other element which is part of a meteorite. That is where the beauty comes. Okay, using some other element, right, some other decomposition scheme of some other element, which I'll come to very soon, we can actually be understanding the age of some part of the universe, such as the age of the solar system, etc., etc. I'll come to that in a bit. Okay, is that clear? So why did we have this detour? We had this detour so that I could tell you precisely that, followed by using the idea of radiocarbon dating. A similar idea could be adopted in the field of astrochemistry to determine the age of some part of the universe. Okay, so the same idea of radiocarbon dating heavy metals, noticeably, the 238 isotope of uranium, right, present in meteorites, to determine the age of some parts of the universe. Okay, I'm not talking about the entire universe. So determine the age of, for example, if we talk about the meteorites that fall on Earth, right, they must have been asteroids which may have been orbiting the sun at some point in time, right? Because they all came up from the giant molecular clouds which were involved in the formation of the sun, right? So therefore, while we cannot completely estimate the age of the universe itself, that goes back all the way to cosmology and the Big Bang theory, we could definitely use meteorites to estimate the age of the solar system. Why solar system? Because the meteorites which fall on Earth may have been very likely, may have come from an asteroid which was orbiting the sun, right? So that's why when we study the nuclear chemistry of the meteorites, in particular, some elements present on it, such as like uranium-238, we can actually understand the age of the solar system. This is one extremely important application, coming from the nuclear chemistry of the meteorites. Please note it carefully. Okay, so what is the nuclear chemistry that is happening in the meteorites via which we can understand the age of the universe? It is that your 238 uranium undergoes a sequence of alpha and beta, beta ray dissipation, right, to give rise to your 206 lead. I mean, this involves many steps, okay, through a series of alpha and beta decays. Okay, so this is an unstable nucleus which has a half-life time of roughly, the half-life time is close to 4.5 billion years, okay, which is of the order of 4.5 into 10 to the power 9 years. And this is stable in the sense that its half-life is much more. Now we can see a pattern, right? See, if the half-life of 14 carbon was what? Of the order of 5,000 years or 6,000 years. With that, you could analyze samples which are as old as 60,000 years. But with this particular specific isotope of uranium, with a half-life of 4.5 billion years, you can understand the age of the solar system itself. So, with this transformation, so whose T half is much greater than the T half of uranium. Okay, that's why it's stable. When you say stable, see, this can take me on a detour of nuclear chemistry. I won't do that. This contains a so-called magic number of neutrons and protons. So that's why this is extremely stable, the 206 lead. Okay, so by this transformation of U238 to 206b, we are a series of there were lots of reactions, some alpha decays, some beta decays. Okay, involving thorium, plutonium, palladium, etc., etc. It's a 16-step reaction. 16, I would say, the chain of these reactions involves 16 steps overall. Okay, but nonetheless, this is the finally formed product. So from the ratio of the 206 lead present in a meteorite, okay, from the ratio of 206 lead, I would say not the ratio again, sorry, from the amount of 206 lead present, you can determine how much of 238 uranium should have been there. Okay, can find out how much of 238 you might have been there in the beginning. When I say beginning, during the formative stages of this meteorite or asteroid. Begin with, and therefore the age of the meteorite could be determined. Could be known. So what I've written here is, from the amount of 206 lead present, we can find out how much of 238 uranium might have been there to begin with, and from this, the age of the meteorite could be known. The age of the meteorite could be known. It's written in the bottom part with a bad handwriting, so just telling precisely what I've written. Now, see, but how is it actually done? What is the math involved? It is reasonably straightforward. I'll give you a brief glimpse of it. Let's say, your 238 uranium is undergoing some kind of a decay. It has been found by experiments, experiments which measure your radioactivity, right? I think it's called as a Geiger counter or something. Okay, so one molecule, right, of your uranium undergoing radioactive decay, it has been found that when n is the number of atoms, or not molecules, atoms in this case, number of atoms of uranium undergoing radioactive decay, for a very small interval of time, right? This has been found to be where K is my radioactive decay constant. So at any given point of time, right, the number that is changing is proportional to the number of, the amount, all right? So the proportionality constant is something K, which is called as the radioactive decay constant. And there's a negative sign to, so that the dimension, so that sign wise it makes sense. Because when we talk of a change, right, we talk about final minus initial, right? So therefore, because as it undergoes radioactive decay, this decreases. So once you have this, we can just rearrange this, right? So this implies this is for a small duration of time. dt is infinitesimal. So for a larger duration of time, we can of course, bring this n over here, is minus k dt. And if we start with n naught at, to begin with, and nt as the number of amount of atoms present at time t, and this is between 0 and t, right? We get, so this is the infinitesimal process. And once we integrate, assuming it's a continuous process, right, we can integrate it. So this implies that I get my n at any point as n naught times e to the power minus kt. This is going to be ln n. So ln of nt by n naught is going to be minus kt. So I just exponentiate it. All right. So following this rule, so from this equation itself, that is like equation 1, if you consider in equation 1 for n naught to become n naught by 2, the time taken is going to be your this is what is t half, right? The half-life time, n naught to become n naught by 2. So see, this equation is going to be the same. Here, this is going to be n naught, and this is going to be n naught by 2. So because this is n naught and n naught by 2, in this expression, both the n naught are going to get cancelled out. And then you can figure out that, and then your t is going to be t half. Okay. So from this, your t half is nothing but ln 2 by k, right? The 1 by 2 is going to be there, and that's going to be the ln 2 once you take this. It is independent of n naught. This is an important point. So because your t half is independent of n naught, once you determine t half, right? Once you determine t half, you can determine your n naught. So once you determine n naught, currently you can calculate nt. The nt could be calculated from the current time. If like U238 itself is not there, right? This much amount of U238 should have transformed into this much amount of lead. So from this you can calculate nt. Okay, so nt could be calculated this way, and using the half-life, your n naught could be calculated. So using nt and n naught, you can ultimately calculate the time, which tells you, how old a meteorite is. Are we clear? So in this equation, there are 3 unknowns. So of the 3 unknowns, your nt could be calculated by the amount of lead that is present. So this much amount of lead must have come from this much amount of uranium. And then your n naught could be calculated by your half-life calculation. So from the half-life calculation, you could get n naught. And so knowing both of these, you can calculate t. So this is how the age of a meteorite could be determined. On that note, in this lecture, what we saw in this lecture today was how the nuclear chemistry of the meteorites could be very useful in understanding the age of the meteorite. How this is connected with the age of the solar system itself, we'll continue with in the next class. And in today's class, we also saw about the fundamentals of mass spectrometry. When I say a very brief overview of mass spectrometry, which was useful to identify the composition of meteorites. On that note, I end this lecture. Thank you so much.